Today we begin Chapter 17 Electrochemistry notes, and we're going to start off by talking about the Statue of Liberty. You've heard the word oxidation, I'm sure, in terms of metals, and what that originally meant was that they would gain oxygen. So if we take the Statue of Liberty that was made of pure copper, it looked like a penny at one point, it combined with oxygen in the air, and then the copper went up to a +2 charge. So originally the copper was at a 0 charge, and the oxygen was at a 0 charge. They were both elements by themselves with no charge. And then the copper went up, so that was oxidized. So it not only was oxidized because it gained oxygen, but also because really its charge went up. At the same time, the oxygen, who had a charge of 0, went down to -2, and so that was reduced. So the copper was oxidized, and the oxygen was reduced. So the actual foolproof definition is that reduction means you gain electrons, which means that your charge goes down. You could possibly lose oxygen, but that's not guaranteed. Oxidation means your charge goes up, which means you would lose electrons, and you could gain oxygen. A nice thing to remember is Leo the lion says GER, lose electrons, oxidation, gain electrons, reduction. So what you need to do is look at the standard reduction potentials, or SRPs, on page 796 in your textbook, or the periodic table reference packet for the AP test also has a chart of all these standard reduction potentials. Anytime your voltage is positive, you're going to be a spontaneous reaction. Now don't get that confused with delta G, because delta G was a negative G to be spontaneous. This is a positive E to be spontaneous, and the opposite, a negative E, will be non-spontaneous. So first we're going to look at spontaneous cells, and then we'll look at non-spontaneous. Spontaneous, the voltage is positive, and this is where you're going to take chemical energy and change it into electrical energy. Essentially what we're dealing with are batteries. This is essentially what we're dealing with. Any battery-operated thing that you're using, whether you're using your cell phone right now or a laptop that's on a battery power, this is what's happening inside that technology. You're having chemical energy inside that's changing into electrical energy that's powering that device. And you could call a battery a galvanic cell, a voltaic cell, electrochemical cell, chemical cell. They're all basically the same thing. The first thing you need to realize in this one is that you have zinc and you have copper. So you need to look at the SRP chart, either in your book on page 796 or in the reference packet of the AP exam packet, periodic table, and you're going to find copper and you're going to find zinc. Now you're going to find that they're both listed as reductions. That's why it's called a standard reduction potential chart, because every one of them has electrons on the left side. So if you look for the copper +2 on the left side changing into copper, you'll see that that happens with 0.34 volts. And then if you look at the zinc, you'll see on the chart that it's negative 0.76 volts, written backwards of this. So the easy way to remember it is to get a positive voltage. The one closer to the top of the paper stays the same, and the one lower down on the paper switches. You only switch the sign of that one, and so when you add these, you're going to get a positive overall number. The other thing you have to remember is that the electrons have to match. In this case, they did already with 2 and 2, so that's fine. But if, let's say, this was a 3 and this were a 2, then you multiply this by 2, the whole thing, and multiply this by 3, the whole thing. But you do not multiply voltage. That's very, very, very important. Do not multiply voltage ever. You only just change the sign. That's all you ever do. Okay, so let's look at the picture and see what's going to happen. This says that copper +2 ions are going to change into copper, while zinc changes into zinc +2. Let's start with the anode. Typically, the anode is written on the left side. Typically. It's not guaranteed, but typically. So the anode, you have zinc strip in a solution that has zinc +2. Over here, you have a copper strip in a solution that has copper +2. You have a wire connecting the two electrodes with a voltmeter, so you can read the voltage. Wire goes to here. Then what you need also is called a salt bridge. It's this upside down U tube. That was the original meaning of the word U tube. It was actually the letter U, tube, because it goes upside down like this. And it's stuffed usually with cotton, and you soak the cotton in some sort of salt that's very, very, very soluble, so a solution of potassium nitrate, and that's going to complete the flow of charge in this whole thing. You can't make it work without a flow of charge or a flow of ions. So here's what's going to happen. You hook this up and it's just going to go on its own. It's spontaneous. The zinc metal is going to dissolve and become zinc plus 2. So zinc solid becomes zinc ion and gives up 2 electrons and that voltage. So now these 2 electrons go through the wire, through the voltmeter, which is going to read 1.10, and then go through here and be on this strip. So this strip is going to become very negative with electrons. So these copper 2 ions are going to get attracted to those electrons and they're going to grab onto those electrons, and now the copper becomes a solid on this strip. So this strip is going to increase in mass because you're going to get more copper here, whereas this one's going to decrease in mass because the zinc is dissolving into zinc plus 2s. Meanwhile, this solution is building up a lot of positive charge because the zinc plus 2 is building up in the solution. So that's going to attract the negative ions of this salt bridge. So the negative ions will migrate to this beaker. And it's easy to remember because this is the anode and the anions migrate there. And this is the cathode and the cations migrate here because all these positives are leaving the solution and going over here to be neutral. So there's less positives on this side. So these positive K pluses are going to come in and replace that positive charge. Again, that allows for a flow of charge, or you could say a flow of ions. Do not say a flow of electrons because electrons are not going through the salt bridge. Electrons merely go through the wire. Another thing you want to remember is an ox and a red cat. So the anode has oxidation and reduction happens at the cathode. All right, so now we learned how to draw the picture. Now we learned how to write the equation using the SRP chart, how to label excuse me, the cathode and the anode. The anode is the negative end of the battery. The cathode is the positive end of the battery. Okay, we can also write this in what's called line notation. So it's just a summary of this whole reaction. Okay, we start with the anode. So the zinc changed into zinc plus 2. So we write that here with a line separating them. And then the copper plus 2 changed into copper. That happened at the cathode. And this represents the salt bridge. And just to let you know, the actual anode is the solid. And the actual cathode is the solid. So in this diagram, the anode is actually the zinc strip. And in this diagram, the cathode is actually the copper strip. Now on this page, we're going to look at an example that's a little different, has a trick to it. We're going to put silver and hydrogen in a galvanic cell. So if you look at the SRP chart, you're going to see that the silver is at 0.8 volts and the hydrogen line is actually 0. So this is the one that switches, which doesn't switch the sign, but does switch the order. And so you're going to see that this is going to get oxidized. Now, the original electron here was 1. This has 2. So you have to double this, double this, double this. Do not double the voltage. Okay, you never double the voltage. You add the whole thing together and this is what you get. So typically what has to happen is you have to have the anode, and by the way the anode's on the right side this time, and the cathode. And the anode has to be a metal. Now since the anode, which has oxidation, has the hydrogen, hydrogen is not a metal. You're not going to have solid hydrogen conducting electricity. So anytime you have an element that's not a metal involved in one of these, you're going to have to use platinum, a platinum electrode. So what you do is you have the wire, again the anode's on the right, the wire is hooked up to a platinum electrode, and the platinum electrode is allowing the conductivity of the electrons, and meanwhile what's happening is hydrogen gas is turning into hydrogen ions. So you have to get an input of hydrogen gas coming into here. This is complicated. So hydrogen gas is coming in, it hits the electrode, it dissolves in the solution and becomes hydrogen ions. Meanwhile, the electrons go through here, through the voltmeter, which is 0.8, out here and onto the silver. Now the silver ions that are in the solution find the electrons and they form solid silver on this electrode. So the cathode again gets heavier. This will not change because the platinum is not involved in the reaction, it's just the hydrogen that's involved. So it's a little tricky, but just wanted to point that out, that you could have a platinum electrode if the thing you're talking about is not going to conduct electricity or it's not a solid. Alright, so we'll move up on the page. Remember what I told you before, do not multiply voltage, only switch the sign if you reverse it. And here's what I just said, if there's no solid form of an element in the reaction, for instance hydrogen, then a platinum electrode is used instead. Now the line notation, remember the anode has to be the first thing, the metal itself, so there is the anode, there is the cathode. Then you have to put both of these because hydrogen changes into H+, and then here you put the Ag+, again this is the salt bridge. Alright, now interestingly you can relate G, E, and K. This is very important to understand because you're going to get a problem somewhere along the line where you're going to have to relate all these together. So the equilibrium constant that we learned about in chapter 13, if you take negative R, T, Ln, K, R is 8.31 joules per mole Kelvin, that's equal to delta G, which you also have to put into joules per mole. And it also equals negative NFE, where N is the number of electrons transferred, so up here it would be a 2. F is a Faraday, named after Michael Faraday, which is equal to 96,485 coulombs. That is the charge. Coulombs is a unit of charge. This is the total charge of 1 mole of electrons. Sometimes we round this to 96,500, just in case you see that. It's just rounded. Okay, so this is the one you really want to focus on. Okay, the standard conditions. You're probably not going to see this one, but just in case you do, this means you're not at equilibrium. Okay, so if you're not at equilibrium, you're not going to have the standard G, the normal G, like the back of the book G. You're going to have like some other not standard G because you're not at equilibrium. In that case, you're going to have a Q. So this is just getting a little more technical. I don't think you're even going to need that one. You should just really focus on this one. This page is a you try it, so what I really would like you to do is pause the video, try this on your own to figure out what happens when you have aluminum in a cell and magnesium in a cell. Draw the picture, write the equations, get the voltage, do everything that we learned on the last page, then restart the video and see how you did. Okay, so this is what you should have found. You should have looked on the SRP chart and realized that the magnesium was going to be the one that switches at the anode, because it was lower down on the chart than the aluminum. It had a lower voltage. So this was originally a negative 1.66 for the aluminum. This was originally negative 2.37. But when you switch that around, it becomes a positive sum for the both of them. You should have realized that the electrons had to be 6, so you had to multiply each equation, the first one by 2, the second one by 3. Do not multiply voltage, of course. And then when you add them together, you would get a 0.71. All right, the line notation, Mg to Mg plus 2 for the anode, Al plus 3 to Al at the cathode. Now, we're going to look at the delta G's. I'm not going to address the purple numbers yet. We're going to come back to those up there, okay? So let's just look at the delta G and the K. Find the equilibrium constant K and the delta G. We learned these equations on the last page. So delta G equals negative NFE. N is the number of electrons, which is 6. A Faraday is 96,500, always, coulombs. The voltage was 0.71. That's what you figured out over here. And this is in joules, of course, per mole. So you can make it negative 411 kilojoules per mole. Remember that a negative G tells you the reaction is spontaneous. Remember that a positive voltage tells you the reaction is spontaneous. So they both agree, of course. Lastly, you can get the equilibrium constant. Delta G equals negative RT ln K. And the G again has to be in joules per mole, because this is at 8.31 joules per mole. And 298 is the temperature, and the ln K, you find it's K is 1.210 to the 72nd. That's a big number. And so a K that is super, super high tells you this reaction favors the right side tremendously. So it's a very, very spontaneous reaction according to voltage. Now I'm going to address the different concentrations on this page slightly before we turn the page to the next page. All the SRP voltages that you look up in that page are based, these are based on a 1 molar concentration of the ion. Okay, so 1 molar concentration of Mg plus 2, 1 molar concentration of Al plus 3. If you start to change these molarities, you will change the voltage. Now let's use Le Chatelier's principle to understand how it will change. If you change this to a 0.5 from 1 and change this to a 1.5, so essentially we increase this from 1 to 1.5, we decrease this from 1 to 0.5. Al plus 3 is a reactant. We decrease the reactant. Mg plus 2 is a product. We increase the product. Now, according to Le Chatelier, if you increase a product and decrease a reactant, you're going to shift the equilibrium to the left. And when you shift it to the left, you're going to decrease the voltage, and it's going to get less spontaneous. So that's qualitative. That's a qualitative analysis of what would happen if you changed the concentrations. On the next page, we're going to get into a quantitative analysis. The last page was more qualitative. This page is going to be more quantitative. Again, the voltage you found is based on the 1 molar concentrations of the aqueous ions, which was that 0.71 volts. Now let's find the actual voltage if, again, the Al is 0.5 molar and the Mg plus 2 is 1.5 molar. So remember what we said? They used to be 1 and 1. Now this is 1.5 and 0.5. The products got higher, the reactants got lower. We know it's going to shift to the left, and the voltage will go down. So here's the equation you need. The new voltage equals the regular voltage minus 0.0592 over N, the number of electrons, times log Q. Remember Q, that test equilibrium? So this one, we're not going to count the solids. Remember, equilibrium constants are products over reactants. Q is like a test because we're not at equilibrium actually, we're just doing the Q. So this is 1.5 cubed over 0.5 squared. We leave out solids, leave out solids. So here's my Q. So I put the numbers in, do all the math. 6 is the number of electrons transferred, remember, from the last page. And look at what this is, 0.71. So the voltage went down from 0.70. So 0.71 went down to 0.70. And that makes sense because, as we said, Le Chatelier is going to predict this goes down. If we want to get this voltage to go up above 0.71, then you can guess we should have made this one higher than 1 and or made this lower than 1. So if we increase this side and or decrease this side, we'll shift it to the right, which means the voltage will go up. All the past pages in this electrochemistry unit have been spontaneous. Now we're going to turn our attention to non-spontaneous reactions. This is where the voltage is less than 0, it's negative, and this is where you do the opposite and you turn electrical energy into chemical energy. So you'll remember that I introduced this unit talking about your cell phone or your laptop maybe on battery power and how it's spontaneous and how it takes chemical energy, changes it to electrical. Well, we all know that after a time, your cell phone and your computer run out of energy. Well, you don't just throw them away. What do? You recharge them. And when you recharge them, that's a non-spontaneous reaction because you're making it happen. And when you stop, it stops. Your phone or your cell phone or your computer will not continue to charge if you remove the source of power or the battery. So now you're hooking up a battery or even an electrical source to make electrical energy turn into chemical energy. Keywords you're going to look for are electroplating, electrolysis, and electrolytic cells. These are all non-spontaneous reactions. So let's talk about electroplating. Electroplating is like coating something with a thin layer of a metal. So let's say you have a key and you want it to look like it's copper, even though it's not, so you want to electroplate it. What you're not going to do is act like this is chocolate-covered strawberries. So we know with chocolate-covered strawberries, you melt the chocolate, right? And then you dip the strawberry in and take it out. We're not going to melt copper in here and dip the key. Number one, the copper, you'd have to get thousands of degrees Celsius. Number two, if you take your key and dip it in the hot copper, it's going to melt the key. So this is not how we do it. What we do is we put copper ions, Cu plus 2s, which you know are blue, and this solution has copper plus 2 in it and then a pure copper anode. All right. So now when you put the key on the cathode, the object you want to electroplate is always on the cathode because that's the negative end of the battery. So this is the opposite charges. See these charges? They switched from the spontaneous. The spontaneous used to be negative for the anode and positive for the cathode. The non-spontaneous is the opposite because you switched it into hooking up to a battery. So this is a negative. Red cat negative, anox positive. That's what you have to remember for non-spontaneous. Red cat negative, anox positive. It's the opposite of spontaneous. So the battery's giving up electrons. The electrons come onto the key. The key is loaded with negative electrons. Copper ions find those negative electrons and come onto here, forming copper solid. So the mass goes up. Meanwhile, back at the anode, the copper is dissolving into copper plus 2, giving up electrons. So really it starts here. These dissolve, give up electrons. The battery is essentially forcing electrons out here, and then by that, it's going to come back in here. So electrons don't flow through the solution, okay? They're only flowing through the wire like this. All right, now let's get more quantitative with this. If you want to know how much copper can be plated onto this key from a copper solution with this current and this time, you're going to use an equation that we call QUIT. Q equals IT. Q is the total charge in coulombs, I is the current, T is the time. Common sense tells you that if you want a lot of copper on this, there's two ways to do it. Number one, if you could turn up the battery current, if you could do that, which you usually can't do that with a battery. So turn up the current. Another thing you can do is just let it run for a longer time. And the more time it runs, the more copper you're going to get. So two variables. But they have to match. This has to be in seconds because an amp is a coulomb per second. If you know that from physics, it should sound familiar. So let's do this calculation. We have 30 minutes, so that's our time. We have to change it into seconds, so here's the conversion. An amp is a coulomb per second, so it's going to cancel out seconds, and coulombs are going to be left. So we got a number of 18,000. So this is going to be quit and then conversion. We're going to convert the coulombs into electron moles. So 96,500 coulombs is always 1 mole of electrons. Now this is key. This is where you're going to be careful. 2 moles of electrons for every mole of copper because copper is plus 2. That makes a difference. If this were gold plus 3 or silver plus 1, then these numbers would be different. Okay, so that's the moles of copper. You could change it into grams, and that tells you how much copper will be extra metal on this key, and the mass will go up by this. So if I give you information for quit, you do that first, then conversions. If I give you information about how much stuff came onto it, how much metal, then you do conversions backwards and then use that for quit. And that's going to happen in the next example. So I'm going to let you try this. You really should try it yourself. First do a conversion. So take your amount of your silver in that case. Take your amount of silver, work backwards to coulombs, then take your coulombs and put them into quit and solve for the time, which will be in seconds. Okay, pause the video. Then when you're done, see if you got it right. Okay, here's the answer. Hopefully you got it right. You started with your conversion. You converted grams of silver into moles. Now there's only 1 mole of electrons for every mole of silver because it's plus 1. And then coulombs from moles of electrons gives you this many coulombs. You take that into quit for Q, and you know the current is 15 amps. That gives you 1490 seconds, which is roughly 24.8 minutes, almost 25 minutes, to get this spoon to be coated with 25 grams of silver from a silver solution. And of course, this was a silver strip. And by the way, here's a cool video that you could watch. All the links in the packet are really good short videos to watch on all the stuff that I'm telling you about. I'm going to highlight some tricky questions on this last page. We'll start off with the electrolysis of water. That means passing electricity through water. You know water doesn't conduct electricity on its own, so you'd have to put in an electrolyte. Let's back up a little bit. Hydrogen, you know, is explosive with oxygen, like the Hindenburg, sadly, exploded with oxygen in the air and made water. It is spontaneous once you give it activation energy. So if it's spontaneous, the opposite is non-spontaneous, meaning water breaking up into two gases is non-spontaneous. In order to make it happen, you have to pass electricity through it, but you have to add an electrolyte, usually sulfuric acid. So the water is the only reactant. What you have to understand is that in water, the oxidation number of H is +1, and the oxidation number of O is -2. So therefore, O here is by itself, it's 0, so this went down. I'm sorry, went up. Sorry, this went up. This went up because the H stayed the same. This is a half reaction, so only one thing goes up. So this is the oxidation right here. And by the same token, here, the hydrogen was +1, and this is a 0 for the hydrogen, so this went down. All right, remember what we have to do is we have to make these electrons match, which we did. Also, we looked up these voltages on the SRP chart. I believe these are on your SRP chart. I'm pretty sure they are. You had to reverse the oxidation one, which I actually listed first this time. So this one got reversed. And when you add these, it's going to be negative, which makes sense because it's non-spontaneous. When you add these, look at what you got. 6 waters, 2 H2s, an O2, and then 4 H pluses and 4 OH minuses. Well, you know these form 4 waters, and 4 waters and 6 waters cancels out to make 2 waters on this side. And so this is your final voltage for this reaction, and it is non-spontaneous. Okay, now what happens if you pass electricity through NaCl? Well, the interesting thing is it matters what state of matter it is. So let's look at NaCl. You know this is plus, and you know this is minus. So plus and minus. So your thought is that the Na is going to go from Na plus to 0. I'm sorry, this should say 0 here. You should get rid of that plus. There's no plus here. So that's a 0. Okay, so plus went down to 0. That's reduction. And then this minus went up to 0. So that's going to be oxidation. All right, that works when it's melted. Okay, you look up the voltages. Here it is, non-spontaneous because it's a negative voltage. And a little note that the sodium solid could actually be a liquid because of a high temperature, and it's very reactive with oxygen or water. All right, so if you had melted salt, this is what would happen. But if you have aqueous, this is not going to happen, because you should recognize that Na solid, group 1 metal, very reactive with water. So the minute you try to reduce this into sodium, it's going to react with the water immediately. So therefore, this cannot happen when it's aqueous, dissolved in water. So instead of the sodium getting reduced, the water gets reduced. So which part of water can get reduced? Remember, it's the hydrogen, because it goes down to 0. So this is getting reduced, whereas this one got oxidized. It went up. This went down. And then when you add it up, you get this overall reaction. Okay, these are just trick questions. So I just want you to see them in case it ever comes up. You'll know the difference. Melted salt, the sodium plus can turn into sodium. But aqueous, that can't happen because sodium metal is so reactive with water, it's not going to form underwater. So instead of the sodium getting reduced, the water gets reduced, and you form hydrogen gas. All right, and I believe that brings us to the end of our electrochemistry packet.